All right, so yeah, so I've got a lot of things. So I've been, made a fresh new set of slides on, for some reason I've just never got around to bipartite graphs properly. So we're going to go through that. There's more to do, but it's a good dosage. It involved a lot of new scripts being created and insanity, so I didn't sleep much last night. This happens with these things. Yeah, anyway, so manic slide product, we'll see how they go, is what I'm saying. They could be not so robust, but I've tried. I have some excellent font choices in there too. So there's Font Awesome. Heard of Font Awesome? Have we talked about that? We've talked about that, yeah. Awesome font. Anyway, it's made for the web, and some maniacs put it, set it up for LaTeX. So Font Awesome is great. You should add this to your Font Awesome. Yes, it's great. So LaTeX has a bunch of icons that are kind of okay, but can you see these? Lots of good things in here, right? So they're very web-centric kind of things. There's some Twitter ones and umbrellas. But they're lots of groovy icons. You can make yourself a little 5-star rating system. Lots of good things. That's where I use the little, go somewhere else link, the link out off the PDF puzzle pieces. I have to use the puzzle piece. There must be a reason for using that. Wow. Anyway, so lots of fun there. Trophies, look at that, great. Yeah. All right, so coolness. So I was going to show you some, look, you guys know about, we'll get to that. You guys know about, networks. You may, yes, of course. What can I say? Right, so this is a course about networks. It's a huge field. We have this character going off to a PhD in network science. So it took a while, it's 15 years, but that's still in some ways pretty quick for a new field. No one talked about networks really in 1998, and then suddenly, oh yeah, there are networks. You're kind of right, actually. But they were hard to measure, so we didn't talk about them much. So there are just millions of papers that come out all the time. Here's one, we've talked about some of these characters before, Christakis and Fowler. Famous for the spreading stuff. It's controversial work, but there are obesity spreads, divorce spreads, loneliness spreads, happiness spreads. But they've done a lot of other work that's quite different to that, and we probably think all those things are true. So this one is using your friends to figure out if some horrible disease is spreading. Kind of makes sense, right? So your friends are different from you, kind of using that in that they may have a horrible disease. So, I think it's a model actually, but that makes sense. These are just things that just appear. That's a different one. This is good. So we've talked about the friends are different from you story. So this is looking at other characters. So it's, the simplest thing is your friends have more friends than you. Extremely disappointing result, right? And this is that they have more publications, they have more citations, right? That just you're in trouble. Your friends are more, whatever. But this has been so this is from Google. It's Google Scholar. But it's a generalization of that. So it gets worse, is sort of the story there. That's one for Jake. Here's a paper. People have been thinking about the airline network for a while now, and we have good data. Hans Hermann is a famous character, so Marta Gonzalez was one of his students. So a nice result here. We've talked a lot about robustness. The story here that they seem to find is that there's a core, all the major airports that connect very strongly, and then there's a big periphery. This is the claim, you'd have to look at it, a big periphery. So you can actually knock out this core, close all those down, and everyone else can still be connected. So that's a bit of a funny result, but it turns out that the outside is more brittle. And I think maybe, one of the things, I'm giving you a lot of basic things, but hopefully it's getting some intuition, that locally a lot of networks, depending on what you're doing, but a lot of networks are branching, if they're more random and so on. So this is kind of getting out to the periphery, and the sense is that you can knock things out there, which is really true in branching kind of networks, right? You can think of the aorta, right? You take that out, you're in a lot of trouble, right? We have a circle of Willis up here, which gives us some redundancy, but generally speaking, a bad plan to take out arteries. Right, trees, not so good if you come off the trunk. So there's it doesn't have that robustness. All right, so that's, that just appeared. What else is good here? This is my little joke. So we have this paper on multi-scale resurgent epidemics spreading in networks of sorts. So it's got a little resurgence of its own. So in terms of its popularity. So that's good. We'll see how it does this year, but it had a little, it's about this basically. Right? This paper, oh my God, this piece. So there's a book, I forgot when it was published, 1996, and it is by this fellow Horgan. And it said it was The End of Science is the title, right? And it's like, well, we're done. A guy sort of most of some details. And this keeps happening, right? So it's not Nobel, but famously, right. It's, what's his name? Oh my God, it slipped out of my head. Lord Kelvin, thank you very much. So Lord Kelvin said this, and he was a very smart guy, right? So he said, he actually sort of apparently said, you really shouldn't get into physics because it's more and more, he may have said this too, like don't go into physics because it's just more accurate measurement, we kind of sorted it out, it's fine. And then quantum appears, right? And I mean, much later, chaos, which just throws the whole mechanics story into mayhem. And many other things. But it's just more and more better measurement. That's where we are. So I guess people come along and say this every now and then. This has sort of been more of the most famous kind of, it's an actual book. So we're done. Actually, a lot of Santa Fe Institute is in the book, as I remember talking about, talking to some of the complexity people. So 1996, networks takes off a couple of years later, so there's a whole field there, of course. But as I've tried to say, systems, the greater part of science will be about understanding systems. We've done it very well with fluid mechanics. That's a huge micro to macro story. But we're starting to understand it in lots of other realms. And a huge part of it, half of it in some ways maybe, is just describing the components. I don't know. It's key. You've got to do it. You've got to figure out what the atoms are. You've got to figure out what DNA is. You've got to find it. Humans just had to one day find that. Or whoever, was in front. It's us, unfortunately. Octopuses could have, right? But we figure that out, and then we march on to understanding how all these things fit together. All right, so anyway, I tweeted this and just put hashtag embarrassing. Anyway. So science is still good, don't worry about it. Okay, some upgrades to all of this. So this is Principles of Complex Systems. Now that's all ordered, right? So this is from the last semester. It's got all this nice structure for the layout of slides and things. So if you ever want to come back to that, which I don't know if you do, but you can. Right, and where we are now, let me go to that one. We are here. Yeah, so, all right, slides are here. So we're up to, I've got to reload this one, I think. Yeah. Okay, so today we're going to finish this stuff, mixed edge random networks. So we talked about that, this generalization of, right, we've gone in all these directions. So this is talking now about correlated random networks. We're just adding this pretty simple thing. It's still random. Correlated random networks, and they're allowed to have directed and undirected links. So that's a pretty good flavor. But we haven't added weighted things, right? With this, there's just a lot more we can do. But that will largely finish the contagion bonanza that we've been experiencing, and obviously partly enjoying. So, and then these are the slides I've just got together. We'll see how they perform, but it's random bipartite networks. It's a beautiful thing, really nice, lovely stuff. Very, again, really applicable, right? Just as we've said, you take Poisson degree distributions, and then that's all fun and games, but you move away from that a little bit and you get to some stuff that's pretty realistic. And the first thing was getting to a degree distribution that's realistic, but a lot of things are just inherently structured as bipartite affiliation graphs. So I'll give you a bunch of examples and then we'll go through some math. And of course there will be generated functions. Okay. All right. Then we'll get on to centrality. Who's the most important node? Is that a good question? not really, but it's something we can't help but ask. You know, we're just like, which one matters in this whole complex thing? Like, which one do I try to sell my thing to? Which one do I try to kill? You know, like that's what's basically, this is kind of the issue, right? Who do I try, you know, if I want, I mean, sometimes it's true, right? If you can get Oprah to say your book is the best book in the world, it's probably going to help. But, you know, if it turns out you paid tons of money to her, everyone is in trouble. All right. Okay, good. So there'll be stories as well. We'll talk about stories. That'll be fun. Right, it'll be stories and tropes. That'll be our little bipartite thing, right? So you'll have your movies, and then your themes and motifs, right? So there are repeated themes. This is just the background, right? It could be anything you want, you know, boards of directors and so on, but that's boring. Or it could be movies and actors, and the paper I'll point to uses that language, fine. But lots of things have this kind of structure. And then there's tripartite structure as well. You can go on. Okay, but that's what we'll use as sort of a fun thing, right? So stories and motifs. Okay, good, right. That's centrality, we don't want that guy, and that's a random, yeah. Okay, I think we're good. All right, if we go. Yeah. Okay, good. All right, so let's just sort of run back over some of this quickly. I've got a few, I don't want to show you all these, but this was just about making sure everything works with the probability distributions. Okay, so here's a key piece now. So now we have some, our degree is in fact this little 3 vector. It's the number of undirected edges you have, the number of edges that are directed coming in, and the number of out-directed ones that are going out, right? So you could switch, if you wanted to switch these to 0 for everyone, you set these to 0, then you've got you back to an undirected one. If you set this to 0, you're in a purely directed mode. So it can shift to those 2 modes, and then it can have this mixed mode that's unachievable kind of just by randomly throwing undirected and directed links down. You can't make this, right? So it's giving you an extra bit of a special facility by being able to specify it. Right. Okay, that's the idea. We're going to get these guys to connect in various ways. So they'll be uncorrelated and correlated. Okay, stop it. We can come back to this if you need to go into that. Madness. Okay, so we're interested in spreading, right? Another fun problem. We'll, with random bipartite graphs, we won't quite get to that. We'll just get to the giant component, which is sort of you can think of as the most sort of as a simple example of spreading. All right. And now from that assignment, I think you have an idea of what happens when you start to mess with, right? If you've got some probability of spreading on top of the giant component, it just atrophies the giant component in a way. It's still the same kind of calculation. All right. Well, not universally, but all right. Okay, so we're going to have uncorrelated networks to start with. We've done this before, and just uncorrelated, undirected networks. So we've done this before, and this is laying it out really clearly. There are different ways to get to this. Certainly when I first started doing this, I would end up with this sum, explicitly this sum, but you know, all of these things were just jumbled around in a way that made it look satisfying mathematically. Right? And this is sort of a failure, actually, to understand the mechanism. And I'll point this out again when we get to random bipartite graphs. So there are 3 parts to it. And the first is, you know, so it's always about edges. So you've got an edge coming out of an infected node. It's tempting to think, well, I have an infected node, how many am I going to infect? That's a very natural thing to think about, but it's much better to think about. Here's an edge that's coming from an infected one. How many new infected edges does it get, potentially, when it hits this person? And really, it's about whether that person switches or not. So if they switch, all of their edges coming out are infected. If they don't, nothing. Okay, so it's this bimodal business. Right, so here's the probability that you connect to a degree, there are no directed edges, to a degree k little u node, right? So there are ku ways to come into that node. So it augments its probability. We've seen this before. This is why your friends are strange, and there's a proper normalization on the bottom. Right, okay, so that's the probability that the edge you are traveling on reaches a degree ku. On the other side of it coming out is this many edges, ku minus 1, right? So these are structural, that's probability. This is a counting piece, this is a probabilistic piece, this is a counting piece, so this is a mechanism, if you like, structure. And then this is the mechanism of the spread. Right, this is about how the thing is put together, and this is about the spreading on top. So it nicely has these two parts to it, network and disease. So, and we'll write it like this, so if one of your friends is on, you have this many friends, this is the probability you switch. Okay. All right, so this is the gain, we'll call these things the gain ratio. This is actually just and so of course we have to sum over all possible, all the probabilities, all the possible situations we could have, right? And that gives us the expected number of new infected edges. We're really averaging this quantity here. And if that's greater than 1, then it takes off, right? This edge gets 1.23 new infected edges, then 1.23 times 1.23 times 1.23. Obviously it's 1 and 2 and 3, but that's the idea. Okay. So it's a gain ratio, it's actually just a number, right? But the natural generalization is out to eigenvalues. Okay. Okay. So if they're purely directed, so we really haven't talked about this, but actually we should be able to see it, hopefully, from this construction. It's kind of a nice thing. So now we have this joint distribution over the in degree and the out degree. And so this could be, a messy, complicated thing, right? So it could be that your in degree and the out degree is the same, and then some distribution over that, or they could be independent, all sorts of things. So there's a lot possible in here. So it all looks the same, except now we can just do things more simply, right? So what's the probability that you hit a node that has an in degree k sub I and an out degree k sub O? Well, it doesn't matter about its out degree because you're jumping on an edge and running along to the end, right? So this is how we select by edge. Jump on an edge, and now it's directed, so you have to go towards the end, the directed end. So there are, for a node that has ki edges coming into it, that's how many ways you can get to it. So it augments the probability, increases it. And we have to normalize by this guy, right? But the thing on the bottom is really, it's really ki, p ki, k0, right? Ko, I should say. It's all of this. For a directed thing. Okay, so it's normalized correctly. So that's your right, so it's the same idea. So we're going to repeat this structure again and again and again. And we'll sort of march out to more and more complicated things. This is much simpler. We don't even have to think about, the fact that we're coming in on one and we have to subtract that away. It's k sub O, right? That's the number of out degrees is specified. The number of out edges. Right. Simple story. Okay. Yeah, so these are the words, right? Probability of connection to a node of a given type, the number of newly infected edges, these two guys, and then the probability of infection. So we're going to see that kind of structure repeated over and over. Again, we have that same b ki, 1 story here. You can imagine it depends on how your out degree as well. It's true. But here in this one, it's just set up as, it depends how many people, they're the ones who are influencing you, right? The ones you influence, you don't care about them. This is an influence type structure. Okay. All right. Let me make it work. Okay, so we're going to have this, we have a growth story. We have one seed, or there could be discrete seeds around the place, but we have one seed, and we're interested in how it grows away from that. And we saw this with the Gleason approach. And so let's just count the fraction that are infected as a function of the distance away. All right, this is a clock running, so okay. in the background. The clock could be all sorts of complications, but basically, yeah, we have this growth, we have this gain ratio that's telling you what the fraction at a distance d plus 1 is, depending on the fraction at distance d. So it could be, you know, some time, different kind of amounts of time elapse between different distances. So we can do all sorts of things. So we're going to interpret these b's as what's the probability that this node eventually infects it, right? It might take 10 time steps or something like that. So given a node is infected, it's got another node here, what's the probability that eventually it infects this other one? Because locally these are branching structures. So we don't care if it happens in the first time step or the second time step, it's just about whether it gets there eventually. Okay, it's a bit of a detail. So there's a possibility for recovery. Yeah. The zombie stuff is harder, where the recovery may involve you know, people helping it recover. So that makes that much harder. So this is a probabilistic recovery. Okay. So we've done undirected, directed. So let's look now at mixed networks. So they have directed and undirected. So gain ratio is more complicated. So we could do this. So now we have, let's keep these guys and let's make these. Right, so here are these are just undirected ones. So the infection could come in through a directed one, and then could leave through undirected, right? Or it could come in this way through an undirected, and then again leave through other undirected ones, or through this directed one. So we're going to blend those two things together. This is cool. So we'll separate into two pieces. We'll talk about the fraction of undirected edges, right, and the fraction of edges that are directed, that are infected at a distance d. Super exciting? No? Okay, it's very nice. Okay, so it's going to look something like this. The fraction of distance d plus 1 and for these two guys depends on what we had at distance d. And now we have to have a little 2x2 matrix. Right? Because, yeah, directed ones are turning into creating undirected, potentially undirected and directed ones that are infected. And so undirected ones, they're potentially creating these guys as well. Okay, so two gain equations. So it looks like what we had before, but it's been spread out. It didn't recompile. I know it's all right. So there'll be a square bracket here. Yeah. Okay, so you see the same things we had before. So this is probably you connect to a node. It's got some three vector here for its ku, ki, ko. This is probably you connect to it along an undirected one. This is how many undirected guys that will be then infected going out, provided the infection holds. And that depends on the fraction of undirecteds already. Okay, so these are the new undirected ones. So undirecteds beget undirecteds, but because you've come in on one undirected one, you've got one less going out. So directed ones, so it's the fraction that were on out edges before, they're now in edges. So what's the probability you connect to a node along a directed one? Same as what we had before. And then any of those out edges, any of those undirected edges, all of those undirected edges are infected, right? Because we've come in along a directed one and we have to count all of the undirected ones. So undirected becomes undirected, or makes new undirected edges. A directed one makes new undirected ones, and here it's ku, here it's ku minus 1. One of the undirecteds is actually the infection edge. All right. Okay, again, should be square brackets around these things. So similar kind of thing, so if you can understand this madness, it needs some more C dots. Yep. Right, okay. All right, so this is the new outgoing edges that are infected. Okay, so it could have come from a directed edge already. Again, it's the same structure. What's probably you came in along a directed edge. This is the number of new outgoing edges that are infected. Just depends on the node. This is the probability you infected it. Fine. If you're coming in on an undirected one, you get the same structure, right? So what's the probability you connect on an undirected one? You get a KO here as well. So both of these guys are the same. KO here, but this is KU and this is KU minus 1. So this looks, right, there's a lot of similarity. These things are all the same. The B's are all the same because it's just one of your edges is infected. One of your potential incoming edges is infected. These guys are the same here. These guys are the same here. These guys, so there's little details there. You can't break them apart as easily. So you can write it like this. Okay, this is the gain matrix that goes up here. Every entry has this same piece. We have to sum overall K still, but we can break it into this little 2 by 2 here. So all of this is encoded into. Yeah, and maybe, no, I don't want to do that. I mean, you could maybe play around with that and make it a little cuter in some way, but basically that's it. So, all right, so 2 by 2 thing, it's an infinite sum of matrices. These are usually fun things to play with, right? In linear algebra, you have lots of good things, right, where you sum up matrices and it works, and yeah. But you should be, you can do this, right? So you sum it up, you get these 4 entries, you compute the eigenvalues. Linear algebra. Yeah? Super good. So that's, and so, right, r squared, r cubed, that's how this thing is working. Boom, 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 boom. So is it growing? So it's a nice little departure from that first one, which was just about, from the first 2 examples, which were just numbers, and if they were greater than 1, the gain ratios were just pure numbers, just scalars. So now we have this thing here. So, it can work in funny ways, right? As long as the eigenvalue is greater, the largest eigenvalue is greater than 1, it's all good. It might be that the undirected edges are really the thing that's spreading things. The directed ones are hopeless. The other way around, right? I don't have to do this, but an exercise would be to see what happens if you turn one of them off, right? So if you turn undirected ones off, just reduce this down. How does it collapse back to the, it would be a mathematical exercise, but how does it collapse back to the conditions that we had on the first slide? All right, it's good. Okay, so let's get to correlated networks that are, correlated networks. Yeah, so it's going to get more complicated. Okay. So we're going to introduce a little bit of notation here, just to kind of, so we can create a series of statements that are all comparable. So we'll do this, right? So this is probably that you end up at a degree k node starting from anywhere. And so this encodes the fact that it's uncorrelated. Because if you're on an edge and you end up, right? You jump on an edge, you go this way, what's the probability you end up at and it's undirected. You're on an undirected edge, randomly chosen. You go one way, you end up at probably a degree k vector node. This says it doesn't matter what the other one is, right? Okay. Similar business over here, okay, for the directed one. And we can do the same kind of thing with this, right? So the probability of infection doesn't matter what that previous one was. It's all about that next node and what's coming into it. So we'll see, this will then, so you can see when it starts to be correlated, these things will take on values, and we'll have to think about them. This is really just what we had on the previous slide, but it now has these conditional probabilities built in, sort of explicitly showing that they don't matter. They don't have any condition, right? All right, that's a notational thing. Okay. This is what we've had so far, and to use that notation for all of them. And to connect them all. So Gain ratio for undirected looks like this guy. The directed, uncorrelated one, it's the same thing, so that we had before, but we're going to put in this structure here. And this is the beast we have for directed, undirected, and uncorrelated. Yeah. Exciting. All right, so let's just see if we can advance this out to the nastier case of correlated ones. You know, and you can see where you stop eventually, right? I mean, it's still elegant, it's still nice, but there's a limit to what you can do with these kinds of, with thinking with simple models. Well, you still get intuition. All right, so now we have to think of where we start. We start from a degree k prime node, we end up at a degree k node. We have to think about that correlation. So this is really basically what's going to happen, right? It's going to depend where you came from. Now there are a lot more edge types. The edges actually have well, that's an interesting thing. There's more structure in the edges. Yeah, there's more structure in the edges. Before it was just uncorrelated. So the edge-edge correlation, that matrix, if you like, is just a product of two probability distributions. Yeah, so it depends where you came from. So it's going to look like this. So I won't go through everything, but you can see the generalization. So before we so this is going to be undirected ones, but they're correlated. So it's just undirected things. Now you'll have a matrix, so it depends where you came from. This is just one term, right? So this is the gain ratio coming from this is just one little piece, right? So this is degree ku prime, degree ku, so this guy's here. This one's on fire, right? They've got the contagion. And what's the expected gain through here? So you have all these different, right? This could be a degree 17, degree 23. You have all of these possible things to think about. Right? Before, if this was a degree 23, it didn't matter where it came from. You just said, okay, there was an infection here. That's all I need to know to compute its probability of success. Now we have to include the fact that we have to count up, get the right weight for how often it comes from a degree k prime node. I know, it's technical madness. But it takes what was a scalar and turns it into so now we have a matrix again. So now this is a matrix, right? So in principle, depends what the values of k could be, right? I mean, you might have a network where the maximum degree is 10. So this can go from 1 to 10, from 1 to 10, right? These two things. If it's infinite, it's a probabilistic sort of story, then this is an infinite matrix. Right, but of course, right, it's going to be some distribution that decays. I mean, it might be a power law, so there are some big things in it, for sure, but yeah. So it's going to look the same, though, right? What's the probability that this infection could have a structure in it as well, so that's going to be a matrix. It's still going to be the case that ku minus 1 new guys come out, but we have to put in that probability of connection. So that's a gain ratio, so you take so all of the edges emanating from degree k equals 1, 2, 3, 4, 5, you've got all of those, right? What's the fraction of infections at that scale? Let's say d away from the source. What is it at d plus 1? Right. So they're all folding across like, yes.
Correlation in the network structure?
Yes. No. Right, exactly. Yeah, right. So this is network structure. And again, network structure, really. And that's the contagion.
And that can also...
It could have some, absolutely. So this could have all sorts of goodies in here, right? So you only get infected by degree 4 people. And so this is all about degrees. I'll show you a little thing where you can generalize it to arbitrary characteristics. Degree plus age plus whatever it is. You can add all these things. Which, starts to make more sense, right? It might be, you connect, yeah. Okay. So the same kind of thing happens when we go to correlated directed ones. right? The fraction of nodes from which the edges are emanating that have degree ki for in and ko for out depends on the previous level, and there's some gain ratio which now has 4 parameters to it, so it's a tensor thing. All of these tensor pieces can be turned into, you can re-express them so that they're basically matrix operations. So it still becomes a eigenvalue type thing. Okay, but it's the same idea, right? So we've got potentially some complicated infection story here, like you were talking about. KO, because it's simple, it's just going to be, if they switch on, it's going to be, all of those guys are out. All of the links coming out are infected. And this is the correlation structure built into the network. All right, so this guy, a little bit nuts. So before we just had a 2x2 matrix. Now we have an infinite set of 2x2 matrices. Okay. So for, it's pretty nutty actually, right? So, yeah. Right, so given you start at some k, this k here, what's my thing? Yeah, there's some gain ratio, right, which gives you what you'll end up with at the next level. Right, it's connecting from k prime to k, we have to sum over all k prime, because it matters where we came from. This structure is exactly the same, except now all the probabilities matter are conditional. So, yeah, a funny business. Before we just didn't have to worry about where we were going to, right? You know, the new edge was just infected. It was just an out edge that was infected. I know this is exciting, right? It's just a fraction of edges that are infected of type undirected or out. Now we worry about where they're coming from. We have to worry about that they're coming from a degree k node or whatever, whatever node they're coming from, because that's the only way we can go to the next level. Yeah, so that's a slightly horrible situation. But you can imagine, so you can take so there's potentially an infinite number of these, you just stack them. So you make a vector. And then this thing will get turned into a big matrix, and this is just a big stack here as well. You could interlace them, whatever you want to do. That rewrites this thing as a matrix, as a square matrix operation. But sort of as it sits, it's a tensor type thing. Anyway, it still becomes an eigenvalue. Okay, so that's it. I just have these slides here to show that you can do some more. So this is a triggering probability, right? So the first thing was just about the condition of spreading. So it was ultimately an eigenvalue story. If it's greater than 1, things spread. This is the next level, which is what's the probability that it spreads. Right, the first one's a possibility. Is the thing greater than 1 or less than 1? It has there's an explicit physical intuition that you use to build that condition, and you use a different one to build the probability one. The probability one can be simple. You can play with it and say, okay, let the probability say the probability is larger than 0. So yes, they're spreading. Let that probability go down to 0, which you've done a little bit with some of your problems, and then we should retrieve the cascade condition, where we should find the point at which things take off. So you can mathematically get all of the previous results. It's just that it doesn't give you an intuitive explanation for it. Okay. I think this is very important, to be honest. Okay, I'm just going to not go into these too deeply, but let me just explain the basic structure. So this is you're on an edge. It's an undirected network. Just the normal things we started with. This is the probability that if you go along you jump on an edge, probably you go and you choose a random end, you go here, that it's part of a giant component, or it's part of a giant infected outbreak. So that has to have a recursive structure, just like we've done with a lot of these things, okay? Which we did with generating functions, but this is just simply a probability. It's one number. So probably that your edge is infected. Well, it has to be this story. It has to have this recursive thing, right? So you could end up, yeah. Right, so you're going along here, you hit this guy of degree Ku. So Q has to be related to, if this is hitting an infinite infected body, then at least one of these is infinite, right? So the way to think about this is Q has to be, you want all of these, at least one of these to be hitting an infinite thing. So if Q is the probability that an edge leads to an infinite network, subnetwork, then the probability that at least one of these does, if there are Ku minus 1 out here, has to be 1 minus Q. That means they all fail. Right? So Q means success, 1 minus Q means fail. It reaches a finite thing. That's all of these guys, right? So all of these ones out here. And then 1 minus that means that at least one succeeded. So it's a very common construction. So that's the beast that's sitting over here. This is the probability that, of course, if this is connected to an infinite component of infected things, then that one has to be infected. So you have to have that. That's this little beast here. And this is the probability that you've run into a guy of degree K sub U anyway. So, you know, you can get to this, again, from more elaborate approaches, but it's very simply laid out. It's a complicated thing to work out, right? This is a nonlinear, nasty business. Okay. But if you let Q go to 0, then there's some Taylor approximation here. We've kind of basically done this, and then you can find when, you know, what characteristics of the network and this guy as well. If you're searching through a family of networks, which one is the one that's right at the critical point? Okay. So this is for an edge. Then the triggering probability is simply, well, okay, given you randomly choose a node, that's this piece, then you have to have at least one of its edges pointing off to an infinite infected piece, which means that it starts the whole thing. Okay. So that's just for undirected ones. You can do this for, and you know, I won't hurt you too much, but directed uncorrelated ones, not such a big departure, because now we just sort of divide things up, right? So now we have, so instead of Ku minus 1, we just have Ko, because there are that many outgoing guys. This is probably that you connected to someone with that, you know, with that incoming degree. And then this looks the same as well, right? Except this is now out degree. So pretty similar. As we saw before, you have to go to these two cases when you have mixed directed and undirected. So you'll have a probability that an undirected edge leads to an infinite infected component, subcomponent. Probably that an outward directed edge leads to an infected subcomponent. And then you have to put these beasts over on this side. Right? So the probability that you're coming along an undirected one, while there are all these indirected ones now and undirected ones. So you need all the undirected ones going out to fail, except for the one you've come in on, so it's the minus 1. And you need all the out degree ones failing as well. But these guys are different quantities now. Undirected and directed are separated. So that looks the same. Before, you know, it would collapse down to 1 minus Q to the Ku minus 1, or just this piece. And this has the same kind of feel to it, except that is not a minus 1 anymore. Super exciting. And the triggering probability, similar kind of thing. You can build it again. Probably you choose a degree K prime node. Then you want everything to fail, which means all of its undirected ones fail, all of its out-directed ones fail, and then 1 minus that gives you probably at least one of them succeeded. Yeah. Don't ask a question.
Like, yeah, the undirected, you subtract one because you come in on it, but why don't you do that in the next?
Here, in this line? Yeah, so because now you're following a directed edge,
Okay.
and the undirecteds are all in play. So you're coming in on a directed edge, but it's one of the k sub I. So maybe you have 7 indirected edges. So you come in on one of those. All of the out-directed ones are possible, right? And all of the undirected ones are possible as well. Right, right. So there's always that little shift there. Yeah. It's probably good. That's, yeah. So, you know, you can do correlated, same kind of thing. So basically there's this, you know, we change to this and we get a sum over where you came from. And let me show you this horrible thing, similar kind of business. And then the worst one of all is this guy. I mean, everything is kind of staying the same, but you can see we've just been able to lift out and say, okay, well, it depends where we came from, and then we have to sum over all of that as well. And the triggering thing is really, that doesn't complicate ridiculously though, right? That's still not so bad. Yeah, that's still not so bad. All right, goody. Okay, so let's just do a generalization just for the cascade condition. So there were 6 families for increasing, or different kinds of levels of complexity. Yep. And it's good to step through them, you know, so you can understand these different ones. And then there's the fully correlated, mixed, directed, and undirected ones. Should all collapse back to all of those other 5 families, but it's good to look at them separately. Okay, so this is the most general approach. It's really just a slide where I'm going to tell you about this. So same sort of thing we've been doing. We have some growth gain ratio. Now it's got these alphas floating around, and they're very general, right? So alpha is this little pair, and it's nu prime, and nu and lambda in general. So nu is all these attributes of the node, and lambda contains attributes of the edge. So it could be anything, right? So it could be the node's degree, it could be its age, it could be whether it uses a Mac or PC. It could be anything, right? Favorite football team. So you put those things in, right? So Red Sox, Yankees, they don't. Or they infect each other, whatever it is, right? So they don't, you know, so you can really, I mean, in principle, you can put anything into this. And then if you have some structure on top, which talks about probabilistically how nodes of, it's really nodes and edges, how those things connect with each other, then, you know, if you can write this down, basically, you're set. So this is about the network, right? So it's the connectivity of the network. This is the property of the network. So this is it's a bit funny, but it's the number of pieces coming out that have nu, and so it's going to be type nu and lambda as the edge. So it's the count of those guys. You know, you have to be careful. Sometimes there's a -1 again, but yeah. That's a little bit of a nasty thing. Right. So again, it's a conditional probability. So it's a lambda prime edge coming from a nu prime node that's encased in this little piece reaches a type nu node, and we're just, you know, you don't really have to put lambda in here as well, but we're just for convenience we put alpha and alpha prime. Bit tricky. So this is the potential number of edges that come out the other side that are of type lambda, given that it came from an alpha prime situation. And then this is this probability of infection. So it's really the same thing, but it's just absurdly generalized. And you get the same thing. So this thing in here, right, this is some big, you make it a big matrix, and you find that, so this is its spectral rate, so it's spectrum, it's eigenvalue spectrum, as long as the largest one, right, largest eigenvalue is greater than 1, then it spreads. All right, so that's a general, very general statement. All right, so we'll finish there. I know it was a little nutty, but yeah, that's a good dig into spreading, where you can really understand it. You know, as I've said, I think that the thing that you go from there is, you know, real simulations, right? But you have and there are some nice little models, and we've produced some, where you do something like you say, okay, nodes have degree 3 or 1, but they're very simple kinds of structures, and you play with assortativity, play with correlations, and kind of see, and I've showed you a couple of examples, see how the spreading condition changes. You know, how does the final size change? So all of those things are good. They can give you good senses of how things work. Okay. You know, I still, somehow there's a gain ratio, whatever the system is, you know, if we're spreading Ebola in Africa for fun, it's a nasty thing, or, you know, the news about Colbert, or whatever it is, you know, like the gain ratio is greater than 1 in some way, and that is a complex mixture of the network of, you know, the spreaders and the property of the disease or the pathogen or the good thing that is spreading, whatever it is. Okay. Okay, good. Okay, so, yep, that's good. I think we're good. That's enough. That's enough goodness. Nasty. I want to talk about, let me get rid of that guy. Go away. Random bipartite, yeah, random bipartite networks. Okay, so let's do that. Good. Okay, so enough contagion. Okay. Right. That was a little painful, I realize. It's beautiful, though. It's very nice. Beautiful. Okay, so lots of beautiful things here. Okay, so right. These are developmental slides. There's going to be more added to them, but we'll have you know, a decent stab at understanding these things. All right. Oh, so now I have this ridiculous little script that sort of just, if you just type a line and it sticks the paper referencing. That only took about 8 hours to make. Okay, and the figure is a bonus piece. All right, so lots of great examples of bipartite affiliation networks. So the thing I want to think about here is there are these induced networks, right? So here's, and sometimes those induced networks are very real, right? So boards of directors is sort of a classic example, right? So you have boards of companies and directors. And so you can imagine them sitting apart and you don't think about the connections between the directors, right? It could come from other sources, which is complicating, but just we'd like to think about how they come from their affiliations with the boards. So if you're on the same board as someone else, you could simply say, okay, then you're friends, you're connected, right? And similarly, you can say that those boards, if they have a person who's on both of them, they're connected. That's a harder thing for us to think about, but it's super important, right? Because, you know, companies and cabinets of presidents and all sorts of things, there are some really interesting kinds of connections if you look at it that way, right? So you look at how the corporations are connected based on the fact that there are people being shared across their boards. They're not all discrete. Because we're people-centric, we tend to think of the projection in one way. So many, many examples. There's just a few I want to show you. So there's YY on, very cool piece. So Jim Bagro is part of this. He's part of our team here. It's with Barabazi. And so this got a ton of press. So this is ingredients and flavors. So it's looking at the atoms, if you like, then, of ingredients, right? So it's all very hard to read, but this is for 2 recipes. These are the things in the recipes. One is a shrimp scampi thing, and I'm not sure what this one is. Seasoned mussels and shrimp scampi and tomato broil. Okay, that's what this is. And the idea is so here are all these flavors. So you have some database that connects things to flavors, right? So this is garlic. This is a sense of how much is in there. So you can see, here's the bipartite affiliation structure here, these little links. And that induces a connection two networks. One is the connection between these flavors, so they co-occur in foods, and which foods share the same flavors. All right. So there are the various ways of doing this. But this is nicely done. So this is the prevalence. This is how big the thing is, the ingredient. So that should be kind of copied from over here. And then this is how many. The thickness of these lines is how many things they share. Right. So this is tomato connecting into Parmesan. Parma. And there's soy sauces up here, right? So garlic actually doesn't have big, thick connections between this. Parmesan, that one is white wine. So, all right. And actually this paper, the story was so they look at this, they play around with this. There's just this plot, but then there's, all right, then let's take a huge number of recipes and do the same thing. This is just one little example. Take a huge number of recipes and do the same thing. And the overall story, if I believe this is right, is that Western recipes tend to match foods. So foods that have similar flavors get put together, or ingredients that have similar flavors get put together. And Eastern ones tend to have flavors that are opposing each other. Sweet and sour is sort of the famous example, right? So, and it's just that's cultural choices, right, that have emerged over time. So this is we'll put in things that, in some sense, clash, like these flavors are opposing, and that's an interesting kind of thing to eat. Or we'll, more of a harmonious kind of structure. So that was nice, a lot of fun, right? I mean, a lot of data, cool thing, millions of citation downloads. This one is okay. So this is now it's the same thing. This is now just taking a ton of foods and connecting them up. So it's ingredients, and then this is the induced network, right? So you have all your ingredients here, you have all your flavors, and then how they're connected by the whether this food contains this flavor and so on, and then you can build this huge connection, huge network. In this case, it's for ingredients. So these are fruits in here, right? So blueberry, cranberry, orange, right? There's some things hanging around here. These guys in here are more, chicken, beef, so this is a meat section, right? You can look at these things later on. This is kind of fun. This is a mushroom one down here. Porcini, mushrooms, shiitakes, just hanging out. Just like, no. We're not going to play. That little complicated one is, fish, right? So haddock and all sorts of good stuff in here. So they, so did a pretty good job, right? Didn't put haddock with milk, which would have been a fail, right? So pretty nicely pulled things. This is dairy over here, so this is just the cheese festival in here. And up here are things like, these are more spices, so peppers and cayenne and this kind of stuff like that, right? So, so pretty well done. I mean, fantastically well done, really cool. So there's that one. So again, right, bipartite affiliation structure. And it may be that, the connections are explicit between the same thing. So directors, they actually talk to each other. Right? The ingredients here, they talk to each other in the sense that they produce a meal, right? But we're inducing the association between them. We're finding that out. Okay, so this is a year, it was published a year later, but it appeared around the same time. So it's Lada Adamic and Yurulin is in here, and I think a student. But they did this nice thing, again, with recipes, but they went the other way, right? So they looked at ratings of recipes and all, other things that correlate. So I think it might be allrecipes.com. Looked at which ones. Right. So now you just have recipes and ingredients, right? So and over here was flavors. So those other guys did this, and this is this story, right? So recipes and ingredients. So the ingredients get connected together through their recipes. So that's one way to do it, and that's what this projection is. Here, there's all sorts of things going on. So they have a number of results. One of them, which I think is not as strong as I thought, but it's that the more cooked the food is, the more people seem to like it. They have, which actually, you know, it's kind of a beautiful story, right? So potentially, I think, right? They cook food. If you're a raw foodist, you won't like this, but cooked food is this. You know, when we figured out to cook some stuff, how to do this, right? Burn some animal protein or whatever, you know, potatoes, you know, cook them up. That we unlocked a lot of things. We unlocked a lot of nutrients, and we also made them more dense, right? So we could bring things together. There are you know, theories that sort of was one of the big advent. And there was all this sort of thing, right? The advent of human society, because now you weren't all just running around the woods trying to find food all the time. You actually kind of had to build a structure, start cooking some stuff here, go and fetch it, but there was a centralization of things. Anyway, but you know, it's kind of a nice little result that they got that out. All right, so that's a fun one. Lots of other things in there. You can play around with that. So Cesar Hidalgo, who's coming this month, will be part of the Macmillan Symposium that we're running. This is, I think, really his first big work, when he was a PhD student at Northeastern. Correct. With Barabazi, yeah. And I know some of you have seen this. This is, so the product space of nations. So the idea that, so nations produce certain products, and you know, there's all sorts of things from oil, fruits and vegetables, to tech, right? So tech is kind of in, electronics is, you know, more central. And they have, so then you can start to associate nations based on that if you want, right? So you have the products and the nations, you can connect them like that. And you can think about how this thing evolves over time. So one of their stories was looking at, I think it was Chile and South Korea. And so you could see where they were on this kind of graph, right? So some places start off often, you know, a developing country might be just, they might have oil for a start, but, you know, minerals and so on. It's not great, but producing simple, you know, foodstuffs to start with, right? And then you can imagine this movement in time as you sort of get to producing higher and higher, you know, more complex things. Some places try to jump, you know, just like let's put a lot of money in and we'll just start producing nuclear fission or something. But you know, the claim was that it's more of the movement is a little more subtle than that, or controlled, right? You are limited by where you are now. I mean, it's sensible. Here's another piece. I mean, it sort of falls into this broad category. Nice study. It's mostly a study. Three of the pieces are academic. You know, it's on academic work. So it's looking at the citations of papers. Right? So you have teams of people who work on a paper, or it could be one, of course, but you have, you know, generally groups, and you can see how those groups change over time. So here it's you know, papers and authors are the categories, or the types, and then you have an evolving affiliation structure. So that's what they're looking at. They're looking at team formation and success. And so you know, this is good stuff. They're quite different pieces because there's economics and astronomy, for example, and ecology, very different, and psychology is in there. But also Broadway, right? So the teams that wrote you know, they've been working on Broadway for 50, 60 years. I think that's how much data they had. Moving through time, you know, people move from group to group, and of course you have very quantifiable success. I mean, yeah, right? Box office success. Here you have citation counts. So they have a model for how this works, but again, nice example. This is human diseases connected by, I think, genes involved in, understood to be involved in the disease. Right? So some disease is very straightforward. It's this one gene, right? And we had this madness. It's a great story of complexity. We had this madness that once we decoded the human genome, we would solve all problems because you just go and switch a few things. But it turns out the more evolution has kind of, you know, sorted that out. So the more complex diseases are often involved in some cases, hundreds of genes, right? I mean, at least that we know about. Like autoimmune things, they're very nasty, messy things. But this is again, one of these affiliation things. So these are diseases being connected with each other. Yeah, I mean, there's everything in it. So obesity is here. This is deafness, leukemia, Lots of different, really quite a broad thing. Okay, so you can see right in this overview, then you start looking at this thing, does it reveal something new? But it's a very natural thing to do. Okay, so, right, and I didn't, for some reason it's not in here. Okay, but the prime paper is a good example of this, right? So you've got the composite numbers and the primes forming a bipartite affiliation graph. So that's exactly the story. Right, so I don't think it's there. Okay, so we're going to work through this paper, which has, I've mentioned before, it's 2001, Newman, Strogatz, and Watts. There's a ton of stuff in here. It's about 17 or 18 pages. It's generating functions, galore, and it's sort of where that gets introduced to the rest of the humans working on networks. Very nicely done. I mean, people have been thinking about generating functions in all other places, but this was just like, okay, now I have some machinery. I will attack this. So here's I'll show you a couple of examples, but this is one projection, right? So 1, 2, 3, 4. It's taken from this paper. So you can think of these as movies, if you like, and actors. And I'll give you another story. But okay, so in this case, so we're going to project. So there's no connections between these guys, right? That's important. It's a bipartite. This is the two pieces, and there are no connections between these. It's induced, and you could think about a probabilistic kind of thing, or you could just make it, fixed. All right. So if it's fixed, it just means that you share the same context. So this context, or I, or whatever it is, let's say it's a movie, so all of these people acted in this movie, so they form a little clique over here. This is A, B, C, D, E, right? So they're all connected to each other. Movie 2 is here, and that's B, D, F, and G. So B, D, F, and G. That's a little clique. Movie 3 is here, and that's only F, H, and I, so that's that little clique there, right? So it's fully connected, it's 3 of them. And G, I, J, and K, they're in their own little piece. And then there's this structure, right? So there's some connections apart from. So if these were all separated out for some reason, there are more people here and they're all distinct things, then these will all be separate components. But of course you start to get this nice overlap. All right, so we're going to figure out what happens if you have an arbitrary number of these guys, an arbitrary number of these guys, and you have a degree distribution here. So in the sense that the degree of this one is sampled from some specific distribution. So you get a 7 for it, and you go, all right, it has 7 links coming down. This one has 3. You create it, or you take a real one, but say you create it like that. And the same story here, it has some other degree distribution, which could be anything. We'll see how they have to connect, but in principle it could be anything. So you sample from that, again randomly, and then you wire everything up, and then you induce the networks and look at their degree distributions. And they're actually so you can take nice, well-behaved distributions, Poisson or whatever it is, and get very complicated, messy-looking ones out for the induced ones. But this is this is a very nice thing, right? You could have actually some nice, clean randomness underneath it, giving rise to some really non-trivial looking distributions. So that's exciting. So being able to pull back from this picture is super important, right? So that's a hard problem. So especially if there are multiple affiliations, right? So this could be people and this is places they work. We've talked about this in POX for the small world search story. You could have multiple kinds of affiliations. So you have A through K over here again, and then they have all these ways of connecting in some other context, right? So this could be their workplace, this could be where they live, right? So they live in the same town, so they have some reason for meeting. It could be over here, it could be religion or sport or whatever it is. That makes it more complicated, but often we just see this, and it's really good to be able to go back to this. And even if we know this, sometimes we just go down here and play around with it, and that's a bad plan, right? We've gotten really stuck for really decades, not just the most recent stuff, in trying to build networks that look like social networks, but only kind of building them in this area, like we want to impose clustering and so on. So one of the things about this is look at the clustering that it forces straight away. And that's, this is a much more organic, natural way of producing that, right? There's a very social feel to it because you've built it in. It's an observation of how many real networks actually, how they're created. Yeah, so there are, yeah. Well, so you have different flavors of links. And this has been around for a while, but there's also now just the idea that you have different functioning networks that are connected in some way. Right. So one example is a communication network overlaid on the power grid. So the power grid's doing something, communication's doing something, but they interact with each other. So things coming from the power grid create some behavior, and it responds and then does something back to the power grid. And that's another whole body of work to add. Yeah, but it's allied. There you really have two networks and then connections as well. So here is an affiliation thing, you're inducing structure. Yeah. So let's stop here and then we'll get into the juicy math that awaits. We'll understand some things, but okay, right. Okay, cool.